Do you ever wonder about what types of jobs are in the space industry? When you look at job descriptions on company websites, do you read the whole thing and still feel confused about what they're looking for? In this video, I'm going to cover different things people in the space industry do. I'll go over 50 jobs, so I'm going to move quickly. If you want to know more about any of them, go ahead and let me know in the comments below. Let's start with what everyone can see, the hardware. Mechanical engineers design the structures and mechanisms most people think of when they think of a spacecraft. Not only are they designing it, but they're making sure it gets built correctly with good drawings and inspection notes. Sometimes you'll work on the flight hardware, and sometimes you'll work on equipment that supports flight hardware, which people call Ground Support Equipment or GSE. Structure engineers are responsible for making sure the mechanical design can survive the stress and strain of all the forces. For instance, rocket launches are violent, and temperatures in space can swing wildly. Structure engineers use finite element models, analyze test data, optimize structures, and make material selections. Harsh temperatures, radiation, and even the thin atmosphere of space destroy all sorts of materials. Material engineers are experts in metals, crystals, lubricants, epoxies, and all the testing methodologies. They spend a lot of time in the lab and help figure out what went wrong when something does break. I'm telling you from personal experience that good material engineers are incredible assets on programs. Composites are tricky and important enough that there are people who spend their whole careers pushing the envelope with these materials. They figure out the optimum number of layers, the way the fibers point, the fiber and epoxy ratios, and the resulting overall properties. They also help procure and manufacture the final result. Space gets crazy hot, and then seconds later, crazy cold. Keeping everything in its happy temperature zone requires things like insulation blankets, heaters, and radiators. They've also got to know how to map and simulate the environments in the orbits and trajectories the spacecraft experiences. Thermal engineers also choose paints and other coatings to get the emissivity and reflectivity of surfaces just right. This picture is of just one of the ISS radiators with an astronaut for scale. Most spacecraft power comes from solar panels that feed batteries, but nuclear power options are starting to become more popular. A big part of this job is managing power cycles when the Earth blocks the sun. They also stay busy with voltage conversions, power routing, and cross-strapping between power buses. Power engineers often work with battery and panel vendors to get the right mix of technology into the spacecraft. Communication engineers first understand all the use cases. Spacecraft can talk and listen to the ground, to other satellites, and to visiting vehicles. They then figure out how much data needs to go over the links and when the links are available. That leads to figuring out the frequencies and power they need. From there, they help get the frequencies they need from the government, buy radios, design antennas, and help integrate it all into the spacecraft. Some communication engineers specialize in ground systems and stations, helping to design and build things like fiber optic networks and robust communication infrastructure around the world. Rockets are given specific corridors they have to fly in or they'll be detonated. Although spacecraft payloads don't usually have to blow themselves up, they do have to prove that they'll contribute minimum risk to the rules levied by range safety. They also have to show that anything toxic, like some propellants, will safely disperse without affecting the population. Range safety experts also run models to show that explosions won't propagate harmful shock waves, even in worst-case atmospheric conditions. Electromagnetic interference can corrupt data or, in some scenarios, destroy the electronics on a spacecraft. The interference can be generated by the spacecraft's own power system, and it can also be created by solar flares and other space sources. Engineers in this area make sure everything is well grounded and that nothing on the spacecraft emits harmful interference. This picture is of a special test chamber that blocks all external sources so teams can measure what the spacecraft is creating. Harmful radiation comes from the sun and from the universe. A single particle from a far-off supernova can hit your electronics with the same energy as if you'd thrown a baseball at them. Radiation engineers help understand the probability of this happening in your chosen orbit by taking into account the probabilities of solar flares and the length of the mission. It would make spacecraft too heavy to launch if they tried to protect all the hardware, but they can help protect the most sensitive hardware. Some propulsion is used to speed up or slow down spacecraft so they can raise and lower their orbits, and some propulsion is used to help twist the spacecraft. There are different types of propellants, including cold gas, hot gas, gas mixtures, ions, and even nuclear options. Propulsion engineers figure out the best option to use and then design the tanks, lines, valves, and thrusters. Fluids in zero-G do things you might not expect. It can make it hard, for example, to get all the propellant out of your tanks when it's sticking to the walls instead of going into your feed lines. Fluids are also important for environmental control for humans in areas like oxygen generation, water storage, and toilets. Side note, space toilets are famous for breaking often. This is sometimes known as attitude determination and control. Whatever you call it, these are the people who understand where your spacecraft is in space, where it's pointing, and how to change those things. They work with things like reaction wheels, star trackers, sun trackers, control moment gyroscopes, and inertial measurement sensors. A big part of their job is writing the algorithms that bring all the sensor data together, and then making decisions about what to do next and how to do it. This is a huge category. Some people focus on spacecraft software, which tends to be C, C++, or Ada. Spacecraft can be thought of as robots in space with intelligence, sensors, and mechanisms that have to operate on their own in a harsh environment, so a lot of thought goes into making them robust. Some people focus on ground systems, making the terminals and infrastructure that routes information and commands everywhere. The languages here can be everything from C to Ruby to Python and HTML with JavaScript. And some people focus on web and design tools to make the company run smoothly. Things like wikis, requirement databases, model-based system engineering tools, and finite element solvers are all big tasks done by hardworking people who are just as valuable, and sometimes more valuable, than the engineers pushing the buttons. Orbital designers create the initial orbit, taking into account what they want to look at and how often they need to see the sun for solar power. But orbits change over time because of effects such as the Earth's funny shape pulling at the spacecraft, gravity from the moon and sun, and the little bit of atmosphere in some orbits. So orbit designers need to think about how to compensate for all that. Then at the end of the mission, they help make sure the spacecraft enters the atmosphere at the right point, either to land safely or to burn up as space junk without hitting anybody. Space is expensive, and you usually get one shot to get it right. Simulation engineers specialize in all the math and algorithms used to figure problems out on the ground. They tend to do a little bit of everything, including programming, graphics, joystick inputs, and network management. Sometimes all their simulations are in software, and sometimes they build full-sized hardware twins of spacecraft to run tests on. This might be a good career for you if you grew up wanting to be a video game designer, but figured out you'd rather get paid more money and work fewer hours in a more stable workplace. It may surprise you to learn that engineers often don't touch, and some may never see the hardware they design. Companies instead hire technicians to assemble things, torque screws, move hardware, fill tanks, set up and take down test configurations, and more. A good technician develops intuition about what will and won't work, so engineers do well to get their opinions on things before they design a new system. Machinists create the parts used on spacecraft. They are experts in machining tools, of course, including state-of-the-art CNC machines. To do their job, they've got to be able to interpret drawings and files. The good ones can spot problems with a drawing and have saved programs weeks, if not months, of schedule and budget by recognizing problems early on. Getting all the materials and parts you need to make a spacecraft is a big task. You need things like aluminum and bolts to be certified to standards with traceability paperwork included. At the assembly level, spacecraft need new, high-tech components built by companies all over the world. Programs can have suppliers that have suppliers that have suppliers. Understanding and wrangling the chaos requires people with an ability to think big and also focus on details. This is one of the most sought-after skills right now. A lot of spacecraft use custom electronics for everything from power distribution to logic and back to communications. Creating layouts requires an understanding of how rocket launches, temperature extremes, and radiation can break things. You've also got to pick the best components and work with others to select the best FPGA and CPU combinations. Field Programmable Gate Arrays, or FPGAs, are used for everything from storing lookup tables to decoding communication signals. They are powerful and becoming more powerful each year. Understanding how to harness that power requires deep understanding and plenty of experience, making this one of the hardest skill sets to find and keep. If you're looking for a job that pays well and will always be in demand, this is the area for you. Avionics usually means all of the computers, sensors, and software in the system. The avionics lead sets the design path for all of those things, and then teams integrate the various assemblies. As an avionics engineer, you've got to know a little bit about everything in electronics, software, operating systems, certification standards, manufacturing processes, and so on. This is a job that's hard to fill because you've got to have significant experience before you're qualified. It may sound dumb, but one of the most common causes of program delays and cost overruns is that engineers underestimate how heavy and stiff space cables are. And it's happened plenty of times that teams deliver something like an electronics box, not appreciating the impact of a cable bundle being attached to one of their thin walls. Then there's the issue that some connectors can take months to get delivered, surprising management that wants to run a test next week. Even medium-sized companies have a department that specializes in making cables. Exquisite spacecraft require exquisite test hardware. The Metrology department is responsible for keeping all the various sensors, power supplies, tools, test hardware, and so on calibrated and documented. NASA, for instance, wants to know how hard you torqued a fastener, and they want to know when the last time that torque wrench was calibrated, and they want the paperwork proving it was calibrated correctly. Metrology often works closely with technicians to keep programs certified and aligned with all the paperwork. Many satellites and spacecraft have optical instruments like telescopes, lidars, and laser communication terminals. Designing the lenses and camera systems that can tolerate thermal changes while being blasted by radiation keeps them busy. Fun fact, many of their designs have tolerances that are measured in nanometers. Understanding how to measure and protect against itty-bitty motions is not an itty-bitty problem. Halfway through. If you're liking this list, go ahead and click the like and subscribe buttons while I drink a little water. Okay, on to the next 25. Test conductors prepare for and run tests on hardware. Some tests can be run in a few hours, while tests like a thermal vacuum run can take weeks, running 24 hours a day, 7 days a week. They often know a test is coming weeks or even years in advance, and they prepare the test facilities, personnel, and procedures. They also request ground support equipment, which itself can be millions of dollars. Gathering all the cables, scripts, test limits, and people requires people who understand how to create beauty out of chaos. These are the people sitting in front of big computer screens. They tend to specialize by area, so there will be, for instance, a thermal mission operator, a power mission operator, and an orbit operator, and so on. Over all of them is the mission director. They help prepare for the mission by creating operating procedures, running simulated missions, and finding weaknesses that they direct the team to address. Being a great mission director requires leadership in stressful environments. These people plan a program out, often years in advance. They map how small assemblies are required before a bigger assembly can be built. Then they figure out when everything needs to be done so the program hits deadlines. Big programs can have thousands of things that all need to be scheduled and flowed into each other. This is another position that requires people who can see the big picture and then drill down to tiny details. Lawyers stay busy with a number of tasks, including managing communication frequency paperwork, getting permission to export technology to an overseas customer, dealing with regulations around facilities, negotiating contracts and non-disclosure agreements, working with vendors, and training engineers not to do anything illegal. They work corporate taxes as you'd expect. They also monitor program budgets and let the program managers know if they're on target or not. All sorts of programs overspend their money, and accountants earn their paycheck by helping to figure out how to address that problem. They also help write proposals by creating and documenting the budget estimate paperwork. Spacecraft companies have huge buildings with sensitive test equipment, big manufacturing floors, lots of chemicals and cryogens, and other things that keep facility managers busy. They are also responsible for the clean rooms, which require strict air filtering and conditioning because it can't be too hot or cold, nor can it be too dry or too humid. They also stock supplies such as the suits you wear in the clean rooms. They do what you'd expect, helping with hiring, layoffs, benefit packages, training, and so on. There's a shortage of them in the industry right now and a real bottleneck to hiring. This may be a good option for you if you'd like to jump into the industry. Recruiters find the talent companies need to bring in. The best ones understand at least a little bit of engineering so they can answer questions from potential candidates. Sometimes they are independent in that they provide talent to many different companies in return for a bonus check paid by the company that's a percentage of the employee's annual salary. This is another in-demand skill that is slowing the industry down. Creating a spacecraft creates gigabytes, if not terabytes of data a day sometimes. You've got all the design files, the test files, all the paperwork, photos and videos, emails, and on and on. Storing and accessing all that data is, to be honest, not a solved problem in most companies. IT folks can also get involved in ground station management and the fiber optic links between them. Different companies and programs treat program managers differently. In some companies, teams hardly ever see their manager, who is out meeting with customers or Congress members or partners. In other companies and projects, the program manager is helping to make day-to-day decisions about the design and maybe even create the budget and schedule. I've been fortunate to have had some great managers myself, and I've also had bad managers that have caused people to leave companies. If you're one of the good ones, companies need you right now. Having a great team and hardware doesn't mean anything if you don't have people skilled in selling things. Spacecraft funding comes from a dozen different government agencies in the United States, and they all have different processes, schedules, and priorities. Commercial companies have their own commercial customers too. Mapping out all these things and networking with the right people is a big job and much appreciated by company leadership. Many government contracts, especially NASA, require big programs to spend some of their money on outreach and education. An outreach coordinator helps create materials and events for the public. They also go to schools and to events to host activities. People who get these jobs love working with people and rarely leave. If you see an opening, you'll probably have to fight hard for it. Most medium to large space companies have an expert or two skilled in building replicas of hardware for public display or even test and simulation. They can get wildly creative with materials and 3D printing. They also help with printing off posters, banners, and other materials for public display. Graphic designers are critical to the way the public views programs and companies. They create renders, charts, videos, posters, and more. And they work for departments like marketing, proposals, and outreach. Often they get designs from mechanical engineers, then they make things look artistic, so they need to know a bit about engineering and a lot about creative design. A lot of companies are competing for a few contracts. You want to look smart and capable with crisp, clean writing where everything is spelled correctly and the tenses are consistent. Technical writers also help pick the font properties and set the graphics in place for proposals. For big events, they can be called on to help create compelling slides and clever handouts. Companies have visitors, customers, and vendors showing up all the time that need to be checked in. Security is also responsible for protecting hardware worth millions and billions of dollars. They're almost always walking around and checking in on things. Programs start with an idea. Mission and system architects are the ones tasked with creating exciting and plausible ideas. They work with all the folks early on in the program, figuring out what will work and what won't. They also work with the sales team to understand what customers are looking for. They usually stay with the program through contract award and then roll off the program to start architecting the next program. Chief engineers have design authority on the program. They are responsible for peer reviewing major design decisions and often help point teams on the right design path early on. When things break, they chair the review board and approve changes. Chief engineers usually have decades of experience and have done a little bit of everything in their careers. Mistakes can and do happen when teams are running around trying to make deadlines. Safety mission assurance engineers are an independent part of programs that create and enforce policies to make sure everything is done safely to improve the odds of mission success. They consider and measure things such as risk, impact of failure, and operation processes. Most companies empower them to stop programs until they're happy that things are done the right way. The quality team are the folks on the ground that inspect the parts and assemblies for compliance with the rules. And they do things like review paperwork, watch tests, and sign compliance documents. They are empowered to stop everything if they see or even suspect a violation. Big programs will often have independent quality assurance teams sponsored by the government to make sure that all the details are correct. Many programs have been saved by someone catching a tiny detail missed by all the engineers and technicians. Big programs also have a team that sets the policy for fault tolerance in case something breaks. For instance, they say how many computers you have to have on board in case one fails. Fun fact, the space shuttle had 5 computers. Figuring out what systems need which backups is a balance between cost, schedule, mass, and mission assurance. Even small programs have someone figuring out what the spacecraft should see when it's in space and analyzing the data it returns when it's flying. Big programs can have teams all over the world that are organized by a chief scientist. They often work with huge data sets to create just a few images that are published for all the world to see. It can be very rewarding to turn mounds of chaos into simple truths. For spacecraft that return to Earth, there's a team that specializes in safely recovering and returning the hardware. This can often mean spending time on boats in the ocean, working with cranes. It sounds fun, and it is, but there's also a lot of thought and training put into every step of their process. Many space companies have offices near the policymakers. So much spacecraft funding comes from the government that it behooves companies to make sure politicians keep the money flowing. This can mean almost anything. Some system engineers specialize in tracking all the various technical budgets such as power and mass. Some manage all the requirements and verification work. Some work with customers and vendors to make sure everyone is hitting milestones. Some specialize in interfaces between systems, such as making sure the power team is talking with the communications team. And some of them do all the little things that come up in a real-world program that you can't really plan for. If there's a unifying theme in all of these things, it's that they make sure all the various disciplines we've talked about are working together smoothly. Okay, that's 50 jobs in the space industry. And there are even more specialty jobs we haven't covered, like spacesuit designers, environmental control engineers, department managers, and transportation coordinators. I hope you can see, though, that there are a lot of different jobs in the space industry. Did I miss one? Do you have questions about the ones that I did cover? Fire away in the comments below, and check out the article I wrote where you can read all of this. The link is in the description.